All right, here we go. Physics reaction video number 37. Looks like I've got some competing face stuff to do, so I'll try to keep myself up in corners or something. So look at this title. It says kinetic friction lab derivation. So maybe it's some a derivation students need to do maybe before lab or after lab. So let's see here. Get started.
Hi everybody, it's Mrs. Cassell. I know that there were some questions about how to use Newton's laws to find the force of friction, and in particular your coefficient of friction in this example. So we're going to go ahead and work through that. I'm going to go over a few things first. The first one being, how do you find a net?
All right, so two cameras. I can't even see the second camera. I'm thinking I would see, oh, here it is maybe. So this, I guess, is the second camera. Very cool. I really like how she's looking at us. And then my guess is she's going to have to look down to right. And this looks like a whiteboard of some kind, because doesn't this look like whiteboard instead of a pen? So I like the setup. And it looks like this was sort of made in response to what students needed. So very cool.
Net force. You may think that you're not solving for net force in here, but anytime that you want to be able to use Newton's second law, you are relying on the fact that Newton's second law says a net force is equal to a mass times an acceleration. So even in a problem like this, where force of friction isn't the net force, it's just one of the forces, you're going to need to find that.
There is a slight delay between the sound and her, like her mouth, you know what I mean? I can't tell if the delay also applies to the second camera. Of course, it could be because I'm recording a recording. Sometimes that happens, but also note that this is a super interesting, it looks like, this totally looks like a whiteboard marker here. Is this a teeny tiny whiteboard marker, or is this actually a sheet of paper? I'm not sure. It's nice and shiny. So cool. I liked what she was saying, though. She's like, hey, you guys, this equation just works all the time. So trust it, right? We can do really cool things with it. So I'm just going to back up so we get the gist of what you're saying and keep going.
Isn't the net force, it's just one of the forces. You're going to need to find that net force in order to utilize this equation to yield its full power. So there's a couple steps to solving
yield its full power.
Any free body diagram, any net force related problem. The first one is that
and I'm sure she's frustrated with this too, that autofocus, right? You get your hand in there and the camera's like, oh, can I help you? Can I focus on your fingers? Let me focus on your fingers because I'm sure that's what you want me to do. So it's so fascinating that cameras these days have just all of this stuff built in. And for this, what we actually want is to set the focus once, be done. I don't care if my hand's in the way. So it'll probably happen a number of times, and I might just grimace every time it does. And I'm sure she's super frustrated about it too. We want to keep the focus right there. I mean, come on, it's a 2D plane. It's like the perfect thing to focus on. And yet the camera has this additional sensor, like, oh, probably you want me to focus on your fingernail instead. So I'm sure she's as frustrated about that as I am. Luckily, I think even when it went out of focus, I was still able to read the handwriting. And of course, as soon as she pulls her hand away, then it'll lock back in again.
Is that you always want to draw a free body diagram.
Yeah, there it goes.
Right? So the first thing you're always going to do is draw that free body diagram. Try to draw it as accurately as you can and include as many details and labels. Second thing that you're going to do is you're going to break your forces into components. So you're going to look at every single force that you have there in your coordinate system. And you're going to figure out what the X and Y component of each of those forces is. After that, redraw your free body diagram, even though that might seem like a redundant step. But if you redraw your free body diagram, it's a nice reality check in the middle of your problem. It makes it easy to see if you've got forces in the right direction, and you can make some estimations about what will happen as a result.
I like that. I like that.
You can also then...
So I'm fascinated by that because, of course, step 3 could just be go back and recheck your free body diagram or annotate your free body diagram. And as you know, when you grade student papers, it's kind of hard to know what was annotated after the fact. So to encourage them to do it a second time in a new place on their page, you can totally see the differences. Of course, video really could be a different way to approach that, right? So the student could go back to the free body diagram and say some more stuff. So certainly I'm a big advocate of students making these sorts of videos too. But no, I really, really like that. A quick comment on the break it into components, right? It's so fascinating how the students are saying, okay, yep, break it into X and Y. And we start with so many problems that have gravity, well, gravity's always down. I guess that's the definition of down, actually. So many problems are flat, and so this is X and this is Y done. And then we start to shift to these inclined plane problems. We're like, oh, well, I mean, you could do that, but you'd be crazy if you called X horizontal and Y vertical. So I wonder if number two, when she's doing those kind of problems, that she adds a little bit, like figure out like the two good directions to choose in the first place. Right. Figure out what a good X and a good Y would be. Make sure they're perpendicular to each other. I mean, you could do this if you wanted to, but oh man, that would make the problem hard. So make sure they're nice and perpendicular, but where should it be? So I'm guessing in this problem, it's probably a horizontal problem. We don't actually know yet. But my question for you guys is, how do you break the idea that X is horizontal and Y is vertical? Like when you shift to the inclined plane, is it just, oh, hey, X is going to be along the motion and Y is going to be the other direction? Or, what's the best way to do that kind of thing? We're just going to back her up a little bit. There we go.
You can make some estimations about what will happen as a result. You can also then easily, graphically or mathematically, sum the forces in the Y direction and the X direction. So you've got sort of this first step here where you're summing the forces, and then forces are vectors. So then you're going to need to actually find net force, which is summing the vectors again, summing force again, right? But
I love the
you
scaffold.
need to find your net force using those X and Y components. Okay.
And what I love about this particular scaffold is it doesn't say plug in here, then plug in there, then press this button, then press this button, right? So that's like uber scaffolded. And honestly, some students need that maybe at the beginning of their study. But these are all conceptually things that, number one, draw a free body diagram. I mean, it's easy to say, but it's hard to do, and it takes some critical thinking. Number two, break F into components. Exactly what I was just saying. Who's horizontal, who's vertical, or is horizontal and vertical the right choices? Number three, redraw the free body diagram, right? If this was just like for robots, the robot would be say, that was the same as step one. Why would I do that, right? But the commentary that she added was cool. Number four, some in X and Y directions is collecting a lot of information. Number five, put it all together in interesting ways. I really like this. Is totally a scaffold, helpful procedure that students can do to work this problem, but it's not like for robots, right? It's for humans who still need to think.
Those are the 5 steps to solving any problem that includes net force. So let's go ahead and go through this process with your scenario that you have here. Okay, you've got a ramp.
Oh, it is a ramp. Exciting.
Like this. Got an incline, whatever it is that you've used. It's at some angle theta.
Whoa! Did you hear that? Whatever it is that you use, this must be some like home project where the teacher doesn't have total control over what they're doing. So every single student's going to do a different angle. Oh man, I love this.
I measured this with my the level on my phone.
Awesome. Let me move my face.
Rather than a protractor. Much more accurate, honestly. And you've got your object that's sitting on top of your ramp here. Now, this isn't a free body diagram, right? This is a picture, but this helps me when I'm understanding a problem. There's a couple things about this lab that are important to realize. It is moving downhill, right, parallel to the surface with a velocity that's constant. So I've got a constant velocity going down the hill. That tells me a few things. That means the acceleration on the ramp is equal to 0 in the scenario that we're analyzing here. So we're going to come back and use that fact to help us. There's a couple other triangle things to remember.
So I'm not sure, right? So that is hard to do. If I said to students, hey, at your house, make an inclined plane and have something go down it at a constant speed, that actually sounds really hard to do. Right, you have to break the static friction and then you have to rapidly adjust the angle such that the kinetic friction is totally balancing the force, the component of gravity down the ramp. So it's a really interesting thing. Like, set it up until you have constant velocity, then let's do some calculations. But I don't know, that sounds hard to do. So I'm wondering if she like was encouraging them to work really hard to do that, or if this is some sort of thought experiment ahead of time. I'm really curious about that. So I'll ask you guys, would you do that experiment? Like, hey, you guys, go home, grab a book, grab a block, keep futzing with it until you have constant velocity. That's hard to do because, first of all, how do you measure the velocity? And make sure that it's constant. How do you deal with the fact that you can't just raise the book up until the book starts to slide, because that just breaks the static friction? You'd have to back off really quick to get the kinetic friction right. So I'm a little bit thrown by that, but let's be honest, this is a super awesome problem, because if you can achieve that, you get exactly what she's talking about right here, which then leads to really, really interesting things. In fact, this angle is going to help us get directly to the coefficient of kinetic friction. So if you can get this to happen, then this angle is this super, super useful piece of information, which is what she's going to get to. Let me back her up a little bit.
Help us. There's a couple other triangle things to remember, right? The sum total of the angle degrees in a triangle is 180.
Cool.
We use that to figure out what some of our other angles are. For example,
smart.
This angle here is 90 minus theta. Right?
Yeah, because that could be useful.
We have 90 degrees here, which means
awesome.
These other two must add up to 180 minus 90.
Assuming we're in Euclidean geometry.
This angle's theta, so I had a total of 90 minus theta. That's what's left over for this angle right here. So those are a few things that we know about this situation. I want to offer you one more.
So I want to point out something here. She has not even started her list of 5 things. Right. So up until now, she's really sort of described the whole situation. And so it's one thing to understand the situation, and it's another to then analyze it. So she's just about ready, I'm guessing, to start doing points 1 through 5 of her scaffolded list. So that's really, really interesting. Just back her up.
Few things that we know about this situation. I want to offer you one more hint in just a moment here, which an angle makes things confusing. I'm going to use this angle in a different way, which is going to help you understand the physics of what's happening here. Okay?
So I'm going to guess here. What I'm going to guess is that she's going to draw this line and this dotted line here and show that this angle here is the same as that angle there. Because of course that's the super important part of this. That's my guess as her big hint, but I love how she set it up. Like, hey, you guys, it's complicated, but I got something to help you. Maybe that she has something else, but it is complicated, so they need as much help as they can get. Let's see what she does.
So I'm going to draw my free body diagram now. So that was just my story problem of the scenario, right? Now I'm going to draw my free body
story
diagram.
problem.
I've
Stupid
got
camera.
my box that's at some angle. I've got a couple different forces that are acting on it. I always start by thinking, gosh, I'm on planet Earth. Force of gravity acting downward.
I love it. Gosh, I'm on planet Earth.
This object is not being pushed. It doesn't have a jetpack in it. It is moving down the ramp because of the net force that's on it, but it is scraping along that surface, so it's resisting that motion with a force of friction that's directed uphill, right? This is parallel. If I kind of draw through here, you know that I've got this angle theta right here. Okay, so that's where this free body diagram, the shapes of this are coming from. It's resting on a surface. So that tells me that perpendicular to that surface, I've got a normal force. So that normal.
So what do we think about a way of writing, because this happens on the chalkboard or the whiteboard a lot too, where you totally block what you're drawing, but you're saying super interesting things, and it's almost like you reveal. So in this case, she can't help it. Her hand blocked everything. We literally couldn't see anything when she said that. I'll back up. Well, no, I'll just back up while I talk here. See, we can't see anything. And then, oh my gosh, right? So what she's adding is this little piece here, which is, of course, super, super interesting, the angle that it's at. When she says all the right stuff, when we can't see what she's writing. Now, some would say, oh boy, let's try to fix that. But I actually think there's something really, really useful here, because for me, like a little bit of anticipation, like, what is she doing? What is she doing? I really want to see. And so I think that there's some value to that. I mean, we could go crazy with technology and make this not work. I mean, the kind that I've never actually tried, but I've seen in practice a couple of times is when you're actually writing on a transparent plexiglass and you're standing on the other side. So the camera, well, let me twist it. Camera's here, plexiglass here, you here, and you're writing like this and the camera's looking at you. Well, that works fine as long as you flip the horizontal of the camera image and it makes everybody look left-handed if they're normally right-handed. That's really cool. You can see everything. And if you watch some videos of people doing that, it's at first you're like, what? It's almost like they're writing in air. No, they're writing on plexiglass. But whew, from a technological standpoint, who's got the time, right? So you got to set up the plexiglass, and you got to flip the camera, blah, blah, blah. So she's already working 2 cameras here because we'd love to be able to see her and her expressions. So I guess I would rather contemplate what are the affordances of the fact that she blocked it. So we could say, oh, what's she doing? What's she doing? Oh, that's so cool. So I'm really intrigued by your thoughts about that.
I've got a normal force. So that normal force is at a 90-degree angle to the force of friction because the force of friction is parallel to the surface and the normal force is always perpendicular. That's
awesome. So I love that. I love that tie in there.
Now we're ready to start breaking these forces into their components. That's our next step as we solve this problem. So,
quick question before she starts. I'll go ahead and pre-back her up. How many of you have worked these problems with horizontal X and vertical Y? Right? Like, how many of you have broken this down so that every single one of these vectors, except for S was gravity, has components? Versus, let's tilt our X and Y to make 2 of them easy and then only gravity is hard, right? Like, is it worth it to show the students that? I have frankly been assuming this entire video that her X is going to be like this and her Y is going to be like that. But it's possible she's going to do this, in which case the normal force and the friction both have to be broken up, but gravity is going to be easy. So I think I'm right, but let's see.
Step as we solve this problem. So a couple things I want to ask you before we do that. First, what's making this object move downhill?
Nothing.
Your
There's no
gut
force.
instinct is to say it's the force of gravity. And you're right. But it's really hard to see that in this situation, right? This object is moving in this direction. The force of gravity doesn't appear to be acting in that direction. Another thing to consider
is a good way to
got one force that's acting straight down in the y
good way
direction.
To motivate this.
The other 2 are at wonky angles. So we're going to have to break 2 forces into components.
Love it.
Which is a big old pain. Unless we turn our paper.
We've talked about affordances, or I did. I used that word like 10 seconds ago. Boom, do that in a classroom. Do that in a classroom. Look at that. This is so cool. And did you see the look on her face? Let's back up. Watch her face. Oh, boom, little smirk. That is so cool. Students can do it. You can do it in this case. You can't do it on a blackboard or a whiteboard, you know, a mounted one. You could have all your students tilt their head. Because, you know, this problem looks exactly like when you're dragging a box. In fact, I did a reaction video just the other day where it looked like this and just this force here was actually, I guess, kind of up and over this way, right? But imagine dragging it on a wire or something. God, I love that. All right, let's go back. Let's let her do that again to us.
We turn our paper. You turn your paper. Now my force of friction.
She's so proud of it. She should be.
In the X direction. Now my normal force is pointing straight up in the Y direction. Those 2 you can easily see are 90 degrees opposed from each other. And only one force is pointing off in a random direction. That's the force of gravity.
That's so cool.
If I turn this
and quickly, before that, she motivated. She said, well, you know, what's the direction it's traveling in? Because that's a 3rd vector that's not represented in a free body diagram. Sometimes the net force will show up there. But remember, there's no net force in this problem. because the acceleration is 0. So she motivated this choice of X and Y by saying that there's this fourth vector we haven't even really talked about, which is the direction of motion. So sometimes I'm critical of free body diagrams because they don't tell the whole story. But what I love is she's got both of it. She's got the whole drawing of what's happening in real life here, and she's got the free body diagram. So she can clearly say, oh, this vector that I drew over here, it would be right along here. So for the purists who don't want non-forces to be in free body diagrams, they would say, oh, don't draw it because then they'll think it's a force. But at least in a video, right, you can say, oh, these are the same thing. So, man, I just thought this was so cool. And then the idea that she said, well, wow, man, 2 of them are easy and only 1 is wonky. Man, that was cool.
This helps answer both of my 2 questions I just raised. I'll be able to break only 1 force into components, right? That's my only task here. I only have to break the force of gravity into an X and a Y component in order to find the net force on this block. And my first question was, is it really gravity that is pulling this object downhill? And here we can see that that's true, right? We've got a Y component. Oh, wait, hang on. That was super crooked.
That's exactly what I was thinking. I was like, is she going to leave that? Is she going to leave it? Oh, it is a whiteboard. You can tell the way she's erasing it. It is a whiteboard. Man, these are super cool, super skinny whiteboard markers.
Component.
Nice.
Equal and opposite to the normal force.
And here comes her hint about the angle.
Let me make my normal force a little bit bigger here, just to have that vector be approximately equal.
Again, anticipation. Her hand was blocking it. What we heard her say is, let me make my normal force a little bit bigger. And honestly, my first thought was, you can't just spontaneously change the magnitude of a force, right? Because sometimes the free body diagram magnitudes are the strength of the force. And so we did, I was like, is she really making it longer? And then her hand went away. So here she is. I'm going to make it bigger. And that's actually all she was doing was, well, maybe it's a little bit longer, but mostly she's just made it thicker so you can see it.
So I've got a force of gravity in the Y direction. And
cool.
I have a force of gravity in the X direction.
Nice.
Now we can see, yes, the force of gravity is what's moving this object downhill. Look at what's happening here. Here's my direction of motion. And which force is acting left and right? The force of friction and the force of gravity.
Whoa, did you see that? Look where she's looking. Look at her. She's looking at us. She's not looking down. Man, so she's actually using the coordination of her pen, seeing her pen in the video so that she can look at us. So it's so cool, because if she were to look down, it would be probably slightly more accurate, but then she'd be looking down. Let me back that up a little bit more again.
Force is acting left and right, the force of friction and the force of gravity.
Yeah, look at it.
So this
looking
force
at basically us, looking at her screen,
moving.
I'm guessing.
We know a couple things already in advance of solving this problem. I'm going to turn my paper back while I write it in.
All right, I'm going to have to bring this to a close. It's gotten a little bit long. So she's done some amazing things in this. She's really sort of set up, hey, trust me, this is a way to solve it. Here's an approach. I actually know, I only got to the first step of her 5 steps, but it got a little long here. But wow, the X and Y choice, the helpful hint about the angle, which she's just about to do. She's just about to say that this is the other angle. I've really, really appreciated that. Multiple camera stuff, the frustration about the autofocus, the tiny little skinny whiteboard pens. Man, there's some really, really, really cool stuff going on in this video. So yeah, I'd love to hear from you guys about your XY choices and how you motivate those. Whether you ever take your chalkboard down and do that. Man, that was super cool. All right, you guys. Well, have a great day. And remember, physics teachers are awesome.